future of artificial intelligence is raw bytes as input and output. Right now we are using tokens, text tokens, image tokens, just because it's more efficient and we don't know how to use bytes. But the whole digital world is in bytes. Byte is universal data type for digital world. It's the lowest common denominator. You can express everything with bytes in digital world. And everything is made of bytes. And we will use AI to detect and learn patterns in bytes. To do this, we need to first understand bytes, the data distribution. What's happening with bytes in text? What's happening? What patterns are there in text, in images, in video, in music? What I'm doing now is I have these 6 numbers, 0, 3, 2, 5, 2, 8. This means 3 plus 25 equals 28. So my neural network will take 4 numbers and output 2. This is just how I structured it in a simple way right now. So before we go to the code, we can just go through this data. We got 0, 3, 25. So the result should be 28 here, but it's not. We got 15, 20, it should be 35, it's 34, it's very close. And 7, 8, 14, it's actually off by just 1. My goal is to see patterns in data. First, let's train the small model, then we're going to understand how bytes exist in this data and see patterns and try to understand it. We're going to use topological analysis, maybe some math tricks, maybe plot the bytes on coordinate systems. We want to understand patterns in bytes so we can design better models. Is it diffusion? Is it autoregressive? Is it something else? We'll see. I told it to generate 10 times more data. Let's see if it's gonna learn better. Even with 10 times more data, it's not able to do it. This is not okay. So I'm just gonna use PyTorch instead. Sonnet was not able to code it. I have some issues. It doesn't work. But Opus instantly coded it. It works well. But I just also gave it a simpler prompt, just addition. And now I'm gonna tell it to teach to input bytes. Now I want the neural network to process input and output raw bytes for this task. So I'm using better model, Opus 4.1, and I'm giving simpler prompt, letting it choose how to implement it. Now MSE loss is actually still existing. What is this average error? What? What are these numbers, bro? I'll copy this part and then I'll paste it. I just want a sequence of bytes where each number is a single byte, not this. And I should say each digit in training data is a single byte. Training with raw bytes actually seems to work. So each digit is replaced with a byte. Neural network is not too big, but it's not too small either. 64, 32, 16, 1. So it has 2 numbers as input, 1 is output. It's the next morning, so we are normalizing bytes to between 0 and 1, A, B, and then sum. So now I want to learn more about distribution of these bytes. I want to learn about the data itself. What is the data like? Use persistent homology to analyze these bytes so we can figure out how to make better systems, better AI. I didn't even tell it to plot or to just output numbers. It will decide itself. So it says, let's analyze the byte addition data using topological data analysis and persistent homology to understand the underlying structure of bytes of data. This can reveal insights about how the neural network learns and potentially guide architectural improvements. So it wrote the code and it has a lot of different analysis. So I got a bunch of cool images, but it's a bit difficult to understand. So I know, for example, that this persistent homology here says that a lot of these bytes are far away from each other. Like this guy is far away from other bytes, and these are closer and closer. This is the closest to some other bytes. So in value, like byte number 15, byte number 51 or 52. And this is byte number that's different than any other byte. I think so. Let's see how Claude Opus analyzes this. When designing neural networks for low-level operations like byte arithmetics, understanding the geometric and topological structure of your data can lead to dramatically better architectures. This tutorial shows how to use topological data analysis to inform neural network design using byte addition as a concrete example. Our topological analysis of byte addition 0 to 227 and 0 to 227 gives result 0 to 254, reveals several critical insights. Perfect linear manifold, the 100% PCA, whatever that is, variance tells us byte addition forms a perfect plane in 3D space. So think of byte addition as a landscape. So on x-axis you plot first byte, y-axis you plot second byte, and z-axis is their sum. You get a flat plane. So imagine a perfectly flat piece of cardboard. One corner touches the floor 0, 0, 0. The opposite corner is lifted up 127, 127, and 256. Every point on this cardboard, one addition problem. So principal component analysis asks how many dimensions do we really need. Example, a piece of paper on a desk lives in 3D space, length, width, height, but really only needs 2D, length and width. Height is always the same. Byte addition lives in 3D space, byte 1, byte 2 sum, but really only needs 2D because sum is byte 1 plus byte 2, perfectly predictable. 100% variance in 2D means once you know any two values, the third is completely determined. No randomness, no curves, no warping, just a perfect mathematical relationship. It's like a restaurant bill. If you know the food cost $50 and tip $10, you automatically know the total $60. There is no hidden dimension or uncertainty. Now let's see connected components H0 finding clusters. Here, this is H0 persistence diagram. Think of connected components as separate islands in your data. Imagine students in a cafeteria. Group 1, friends sitting together at table A. Group 2 at table B. Group 3, someone sitting alone at table C, for example. Connected components is three separate groups. So we had 500 sample points that form 499 separate islands with very small gaps between them. So if you plot all of those points on a coordinate system, you're gonna get some gap between them. So they're all gonna make separate points. If you start with same point, then that's a single point. If you have 2 points on the same spot, that's a single point, single connection, single connected component. This tells us that our sampling is pretty uniform, no big clusters, so it's random, so it's spread everywhere. So there is a lot of different components. The separation is happening because of our sampling. It's not inherent structure of the data. So imagine we have some dots and we start growing circle from each dot. And the bigger the radius, some circles will start touching. So they will form a new connected component. So in the beginning, when nothing was touching, every component was different. And so when two circles touch, when we grow radius, then the two components will die and there will be born a new one, connected component. So if you grow circles until infinity, all of them will connect, and then you count how many in total different connected components there are. So If you take 2, for example, there is 3. There is in the beginning 2 separate, and there is the new one when they connect, so there is 3. So in total there is 499 out of 500, which means that some of them could start with being on the same spot, same component, same coordinates. So there is less than 500 actually. That's how I understand it. And then when you grow those, so that's gonna be age 1. So when you grow those circles, sometimes 3 of them might connect and there is a loop. And that's gonna be age 2. A loop or one-dimensional hole, so we just look at the hole in between those connections, happens when data forms a circle-like pattern. And there is no other connections inside of the hole. So as soon as you have hole of 4 circles that are growing, but let's say these opposite circles connect, then there is no hole anymore, independent hole. Although there could be now 2 smaller holes. But if circles connect and there is like some other dot and circle inside, then that's not a hole. Why modular arithmetics create loops? Think of a 12-hour clock. 11 plus 2 hours is actually 1, not 13, because it wraps around. So what these holes mean is that there is some forbidden type of data, or less likely or difficult or unreachable type of data, or maybe some operation. But I'm not sure, because when the holes, like when the circles around every dot expand, they're gonna cover everything, so I'm not sure. Then we have error distribution, boundary struggles. What are boundary errors? The neural networks makes its biggest mistakes at the edges of the input range. So 0 plus 0 or 127 plus 127. But 0 plus 0 would mess with the neural network because you're multiplying weight by 0, so you will get a 0. So if you have 0 plus 1, yeah, well, zeros are messing with weights because they nullify them. So we have fewer training examples at boundaries, that's why they struggle. One-sided learning. For values like 50, you can learn from 49 and 51, but 0 can only learn from one side, from 1. And it's missing context from the other side. And then the ReLU activation function could mess with numbers near 0. This is it. Look. Look how circles are growing, and when they overlap, then components connect. It turns out that persistent homology is well suited for detecting structure in high-dimensional datasets. So it is no surprise that the technique has mostly been applied to cosmology, to either, but we can use this for AI. They use this to see patterns in stars, but we will use it to see patterns in our bytes. Stars and bytes, those are like 2 most interesting things. Interesting animation from this notebook. Look at this. So these components grow, and when they connect, they die. So this is death. And then, so as soon as the 2 components connect, both of them die. And this is radius. And now this one, these 2 dies, and they connect here. This is what it looks like. Here we have a loop. This is just a connected component. Here we have connection across the loop, which is going to nullify both of these loops. Now these are no longer loops. If there was no disconnection that cuts them, then they would be loops. So I see that this looks like a loop as well. I'm not sure why this is colored in and this is not, but this looks like a loop to me as well. I'm not sure here. Let's see again here. So growing disks, we have, when they merge, we have this death at the radius. And they all already died. And now it's also showing birth. So actually here, if they are on this line, it means they get born and die at the same time, which means they are not persisting. Because they merge and then they merge with something else and it kills them instantly. And then if they are far away from this diagonal, that means they are persisting for a long time. So whatever this one was, this pattern here, I'm not sure which one it was, but that pattern was persisting for a long time. So that's a pattern that we discovered in data. That's there for a long time. So I understand this guy explained on this YouTube. So you see there is big circle around, and once it fills in this part, white part, then it will die. You see this one that I was explaining, it died here once it fills in this part. So you can check this. What is persistent homology? This is a real world data. This looks very interesting. Maybe we can do this with our bytes. So this shows that most of the components die as soon as they're born, but there is some components who persist. Maybe we need to discover which ones persist and then design neural network based on this. I'm not sure exactly though. And such a good thing about AI is we don't need to like go into the real world and collect blood samples, buy some steel, generate data, look at the stars. We can just generate so much data instantly. It's digital. Everything is so fast. Everything is so easy. So now I have this text, and then I'm analyzing it with bytes. I'm analyzing its bytes with persistent homology. Now let's analyze it with the help of Gemini, because I don't know how to analyze it so well. So it reveals that text is highly structured and non-random, the bytes of text. The rules of grammar, example, letters form words, words are separated by spaces, create distinct predictable patterns that can be seen as clusters, paths, or rhythmic signals in the data. The topological analysis confirms that at a high level, the byte patterns form one large interconnected structure with no significant holes or voids, which is characteristic of a coherent language. So holes or voids would mean that there are some forbidden ways to speak this language or something, but or impossible ways to express ideas. As I understand, the language, it's very malleable and you can arrange it in any way you want. So there is no so much holes or voids. We have this byte value distribution. You see a lot of, this is space, I think, very frequent. And then we have these small case letters, very frequent as well. So it's A to Z lowercase. So character type distribution, letters a lot, then spaces a lot, a few digits, a few punctuations and other. Then we have these consecutive byte pairs. So this is space. You see, space is after a lot of letters, a lot of other characters. So this is space, and then these are all of the letters. And here, space as the second byte, and letter as the first byte. And here this is space as the first byte, down here. So it's paired with a lot, and we also have a lot of pairs of small character, lowercase A to Z. And then we have a byte transition matrix. For example, Q is never or rarely followed by Z, so those would be black. And then red is when it's more common. If we had random text, this would all be colored randomly. If we had random bytes, I should say, or yeah. And consecutive byte triplets. So 3 bytes appearing next to each other. And you see we again have clusters, probably of small letters. And then space is some of these. Here we have these age 0 connections, component connection that I was explaining. So a lot of them die early. So you see they all get born instantly, but then they die. But then this one is persisting for a long time. For example, that could reveal some patterns in data. It's very far away from the diagonal. And then loops actually exist for a lot shorter. And then voids don't even exist. Void is when you have, as I understand, 3D space. And that's circled with other spheres. It's like this ball, this sphere, and there is nothing inside, but it's completely circled. Inside topologically, the text's byte pair structure is simple. It's a single connected blob. This is a powerful mathematical confirmation of the cohesive and interconnected nature of language patterns. I think we covered a lot this video. I'm gonna leave a URL to this collab below. I'm not sure what to do with this. I'm gonna keep exploring this area and other areas. Some of you wanted to contribute to my GitHub open source AI. So besides these courses or free courses on building these large language models from scratch, I have these research projects like figuring out FP4 pre-training and multi-GPU and stuff. But I'm not sure. I want to make this so anybody can contribute, even beginners. Maybe I can figure out some tasks that are for beginners or something, but I'm not sure yet how I would do this. I guess just create a bunch of tasks and then let people choose what they find interesting or something. I'm just not sure what I can do for beginners. Maybe some simpler tasks that they can code or something, but that needs to be valuable. And so I can create a Discord group as well. So give me your ideas below how I can make these tasks, how I can enable beginners to contribute as well. Check out other videos on my channel. You can learn about AI research and everything. And see you next time.